When we translate rate information in a word problem into a formula, the phrase continuous rate has a very particular meaning in science and mathematics. And it boils down to, if your rate is equal to r, then it goes into the exponent with your time with a base of the natural exponent e. You'll often see this phrase used with chemical reaction, population growth, and anything with interest where the interest is continuously compounded. The alternative that's most typically used when we talk about percentage growth is that you might actually have a measurement where you say, I know that after 1 year I've gained 3%. This would be a typical annual bank rate where you know exactly what amount of interest you're gaining. The model you get there is 100%, which is the same as 1, plus or minus, depending on whether you're growing or shrinking, your percentage change. We take all that and we put it to the power t because we'll get that effect multiplied, say, for every year of a deposit. The difference between these two in prediction for small r's is very, very little. These basically give the same prediction. For bigger r's, there's more discrepancies. The issue we're trying to confront is what kind of information are you provided? Is it provided in the form of a continuous rate, or is it provided in terms of something where you know what happens after 1 year, and that'll guide you to picking one model or the other. Take a look at these sentences here, and we'll walk through each one and just see which model makes the most sense. Infant mortality is being reduced at a rate of 10% per year. Would we model that as an amount of, say, m of t as being 1 minus 0.1, that's the 10%, or e to the minus 0.1 t? Think about it for a moment. In this case here, the way we'd naturally interpret this is after 1 year, or at t equals 1, we have lost exactly 10%. And if that's the case, we would not use the E model, we would use the 1 minus. This will guarantee that after 1 year, we've lost exactly 10%. How about my $10,000 investment is growing at 5% per year? And ask, is my investment value going to equal my $10,000 times 1 plus 5% per year, or is it going to be the 10,000 multiplier for sure, times an exponential 0.05 to the t? In this case again, if all we're told is that we're gaining 5% per year, then that would mean after 1 year, we would have 5% more, exactly 5% more. That points away from the exponential base e and towards the exponential with the base of 1 plus your interest rate. Third, savings account offers daily compound interest at 4% annual rate. This one is on the cusp. So one model would be 0.04 to the power t. The other one would be e to the 0.04 to the power t. In fact, we know up front it's not this one because this would predict exactly 4% growth. But if we're compounding on a daily basis, the interest gains interest. The interest on the first day is going to gain interest for the rest of the year. The interest on the second day is going to gain a little less interest, but it's going to gain interest as well. So we're going to get a net above 4% effective interest rate. This is the closest model for that. But for those who have seen some finance stuff, there's actually a not horribly complicated, but a little messier formula, which is you take your 0.04%, you divide it up into 300, oh my goodness, and then you have t over 365. This kind of thing gets complicated and silly really, really quickly. You can model this kind of interest that way, though. It turns out that this, starting at the base model, going to this model, it actually leads to the exponential model. So that kind of growth is something we won't be doing in this class. We're not going to focus on that much detail. We'll either get something relatively simple like this, where we have growth on a certain time frame, or we'll have a continuous rate, and we'll model it that way with the base E exponentials. Last but not least, bacteria are reproducing at a continuous rate of 125% per hour. The two models we would have here would be 1 plus 125% is 1.25, or e to the 1.25t. Which of those models do you think we would be using given the phrasing and the structure there? In this case, we have that explicit phrase, continuous rate. Very much like daily compound is almost continuous. Here it's explicitly said that the rate is a continuous rate, and so we are going to use this positive base e exponential with the rate times t in the exponent. Essentially, that's the definition of when we use this base e to the power, is when the phrase there is a continuous rate. With that theory behind us, we can now take a look at the formulas we were working on earlier. We have a cup of coffee which has 100 milligrams of caffeine, which leaves the body at, here's that phrase, a continuous rate of 17% per hour. As soon as we have that, we can now write down the model for our exponential. We have our initial amount, A naught, and we have e to the negative RT. It's negative because we're losing the quantity, or losing the caffeine over time. Once we have that model, we can easily make predictions. We have a to the 4, a of 4, 0.17 times 4. If we use our calculator, we're going to get there approximately 50.66 milligrams. So about half of the caffeine is left after 4 hours. How long does it take to get down to 10 milligrams? Well, there what we're going to do is set the A amount equal to 10, and that's going to equal our 100 times e to the negative 0.17t, and what we're looking for is that t value. So we'll have to do some solving in this case here. It's not quite as straightforward as the previous question, but it's not too bad. We have 10 over 100 is equal to e to the negative 0.17t. I like to simplify, so we just have the exponential on one side first, and then we can leave some room, move that over a smidge, because then what we're going to do is take the ln of both sides. That gets us an exponential base e and a logarithm base e, which are inverses. That means we're going to have negative 0.17t left over from this whole right-hand side, and this is 0.1 or 1/10, whichever you prefer. And so our t is ln of 1/10 all over negative 0.17, and that, with our calculator, is approximately 13.5 hours. Again, that seems fairly reasonable. It took 4 hours to go down by 50%. To go down by 50% another couple times should take another 4 times 4 plus 4, another 8 hours. So pretty reasonable ballpark there. Let's make that a little more explicit and find the half-life. For those who are a little bit rusty, the half-life is equal to the time it takes to reduce the caffeine level to 1/2 of the initial amount. And the nice thing about that is it's straightforward to put in. If we have our A is equal to 100 e to the negative 0.17t, then what we're talking about is reducing the amount down to half of what 100 was. This was our initial amount, and on this side we're putting 1/2 of that initial amount. If you have a formula memorized for this, that's totally fine too. We're going to go through the calculations because they're not that burdensome. If we start solving here, we see 50 over 100, which gives us that 1/2. So we can actually see the 1/2 in the calculation. That's the 100 being brought down, leaving the exponential. And in the same approach that we took before, we would take the ln of both sides. Ln of both sides. We would get back to our negative 0.17t is equal to ln of 1/2. And so t is ln of 1/2 over negative 0.17. And again, just conceptually, we saw before that after 4 hours, we got very, very close to half the amount. We expect this number to be very, very close to 4 then. And that is in fact the case. We get approximately 4.07 hours as the half-life. With all that information, we can now sketch a much more detailed graph of the milligrams of caffeine over the time in hours. Here we have 60 and 40 and 20 and 80. We know we started at 100 milligrams at 0 time. And if we go up to 12 hours, we know that after 4 hours, we're a little more than 4 hours, we're at exactly 50%. At a little bit more than 8 hours would be at 25%. And after 12 hours would be at 1/8 of that, which is about 12 and change. And so knowing it's an exponential decay and having that many points on file, we can actually see pretty close the 13.5 hours that we found earlier to reach 10 milligrams. That fits perfectly with the curve that we've inferred using just the half-life alone. So it's a very rich and predictive model for how the caffeine level is going to change over time.